Hello everyone and welcome to today's video where we will go through some of the latest questions from flight planning. So without any further ado, let's just jump right into question number 1. So an aircraft is flying over terrain of up to 2000 feet elevation. The minimum holding altitude or MHA over this terrain provides in the holding area a minimum optical clearance of how many meters? So these will be conflicting with ICAO and EASA. This is why sometimes you'll hear them in feet and meters, because EASA uses feet and the ICAO documents will most cases use meters. However, the altitudes and the distances will be almost always the same. Of course, there are two cases here. One will be mountainous terrain over 5,000 feet, and one will be below 5,000 feet. Below 5,000 feet in non-mountainous terrain, your holding zone gives you an obstacle clearance of 1000 feet or 300 meters. If we're talking about the holding where that is in mountainous mountainous area with mountains of elevation above 5000 feet, then this obstacle clearance is increased to 600 meters or 2000 feet. Here also remember that besides this, there is also something called the buffer zone around the holding area, because these obstacle clearances are only guaranteed in the holding area and the holding entry zone. Anything beyond that, that extends to 5 nautical miles, is called the buffer zone. In there, the obstacle clearance is steadily decreased, and it decreases to almost zero at the edge of the buffer zone, where it gives you only a couple hundred feet of obstacle clearance. In the non-holding zone, however, you do not have that buffer zone. This is why it's always important to stay on the right side of your hold. For the exams, there are a few things about holdings that you should remember. Remember that you always will enter a holding from the top, so the aircrafts will be stuck from the bottom, going up and up and up, and they will also leave in the same order, so the aircraft at the bottom will exit first. Above 14,000 feet, the holding takes 1.5 minutes in the outbound and inbound, and then only 1 minute below 14,000 feet. Also below 14,000 feet, the standard holding speed, maximum holding speed, is 230 knots, something to remember for the exams. And lastly, remember that there are 3 ways on how you can enter the hold. These will be the parallel, the direct, and the offset entries. Now going into question number 2. So during the pre-flight briefing, the commander of a commercial air transport flight notices thunderstorm activity en route that could lead to deviations of more than 50 nautical miles. For the pre-flight fuel calculation, given the deviations would increase the distance to be flown, the commander should. So remember that during your pre-flight briefing, in most cases, you will already have your operational flight plan, which will include the fuels. In that case, of course, you do not change the trip fuel, you do not change the contingency, you will add it as an extra fuel. This is the commander's discretion based on your current information. You can add that fuel for the weather or also for the traffic or for any circumstances that you deem necessary. There are quite a few things that we should mention when it comes to fuel planning. Although the mnemonic that I'm showing you here, the TT Cafe, is slightly outdated, and this is a slide from a presentation we've made some time ago, it is still valid for the exams. So remember that you have all these different types of fuel that are make your block fuel. These will be your TT Cafe, so taxi, trip, contingency, alternate, additional, reserve, and extra fuel. The extra fuel is the commander's discretion. However, there are many others that you should also consider. But remember that the trip is only from takeoff to landing from point A to B. The contingency is for your unexpected situations, such as, for example, holding short of the runway longer than you expect, or maybe different routing that you wouldn't expect, and these contingencies take this into account. However, this is not for weather avoidance. That will fall under extra. This is right before the flight, when you see the weather in your EFB and your weather reports, and then you decide on taking that extra fuel. For question number 3, some procedures are designed as RNP authorization required approach. Which of the following is an example of how to identify on an instrument approach chart a procedure necessitating this designation? By definition, your RNP authorization required approaches will have a curved final approach segment. And this is what differentiates them from your standard RNP approach as well as your RNP AR approach. These AR approaches, they need two things. They need certification and approval from the authority, as well as they need the certification of the system to fly these approaches. As you can imagine, when you're flying a curved approach, there is a lot more to do as compared to a straight final approach, because here the aircraft needs lateral guidance that is curving before the threshold, and these approaches can be very tricky at times. When it comes to all the other questions, of course, the LPV minima and LNAV minima, these are just two different types of standard RNP approaches. The LPV gives you angular deflection like the ILS. The LNAV gives you lateral deflection, so cross-track. When you fly them, the LPV can be flown to Cat 1. The LNAV is your standard APV approach with vertical guidance that is considered a non-precision approach. And of course, a procedure using a GLS with Cat 1 minimize a standard precision approach on its own. In Europe, we have quite a few curved approaches. One that I wanted to show you here today is a fantastic approach from Nice in France. So Nice in France has two types of approaches for runway 22. One is authorization required, and one is the standard RNP. This is the approach for runway 22 in Nice that requires authorization, that uses the GNSS, and this is an RNP approach, and this is a Lido chart. So if in the future you'll ever fly the Airbus aircraft, most likely this will be the chart that you'll see. However, they work pretty much the same as Jepson. So as you can see here, we have this last segment starting from Mike November 904 that leads us to Mike November 905, and this gives us an extremely short final with an 1.37 nautical mile arc before the threshold. And this is what makes this approach so tricky. This is what makes the approach so difficult for the systems to calculate. And these authorization required approaches can be always identified in the right side, as they will always by law be required to have this designation of AR, standing for authorization required. And now going into question number 4. So given flight level 370, Mach 0.74, outside air temperature minus 47 degrees Celsius, and your true airspeed, what will be your true airspeed? So in this case, there are two ways of calculating this. One, you can use your flight computer, your CRP5, or you can simply use the calculator. I, in these cases, recommend using the calculator. This is how I would approach these questions. In order to use the calculator, you need to know an extremely easy formula, or two of them actually. So the first one is, of course, that your Mach is the ratio between true airspeed and local speed of sound. So if you know the Mach and you know the local speed of sound, then you can easily calculate your TAS. Remember that Mach only depends on the temperature, so the flight level here is only given to distract you. To calculate the local speed of sound, you have to use a very simple formula, which is 39 times the square root of temperature in Kelvin. Remember that the temperatures in Kelvin are absolute, and the 0 is the minimum temperature in Kelvin that you can have, that we can have in the universe actually, and there is no maximum, just to tell you as a fun fact. However, knowing that the absolute 0 in Celsius is minus 273, you can now easily calculate kelvins for any other temperature, as the 0 Kelvin is minus 273, and these temperatures are linearly offset. So minus 47 plus 273 will give you the temperature in Kelvin, 223 kelvins. So 233 square root times 39, and then this times your Mach, or 0.74, will give you the correct true airspeed, which will be 434 knots. And this is why this question has so many comments, is because people trying to do these questions using the CRP5 and flight computers find that sometimes it's much harder to see these small numbers, and they can get slightly different answers, especially when they are very close together. So I highly recommend that you use the formula of Mach being the true airspeed divided by local speed of sound. Local speed of sound, 39 times the square root of temperature in Kelvin, and then you can rearrange the formula to get the true airspeed very easily. And now going into question number 5, which is the last question we have here. Which of the following statements contains all the corresponding altitude and flight level instructions when departing via CATON to Charlie? So if we look at this approach together, you can see that CATON to Charlie, either you can read it here at the bottom. However, looking at it, it's quite simple. We are taking off here, going to 9.5 DME, and then we need to reach, be at 3,100 feet or above. Then to Vilna, where we need to be at flight level 80 or above. Nargo, where we need to be at flight level 110 or above. And finally, CATON, where we need to be at flight level 230 or below. Now, looking at all of the answers here, you can see immediately that there are two nomenclatures that this person who has wrote the question is using, which is one not below and one at or above. The proper vocabulary, the proper standard phraseology here is at or above. So this should immediately raise some bells. And here as well, you can see at or below. And even not seeing the chart, just knowing the standard phraseology that is used by Jepsen, you can already tell that this will be the correct answer. Remember that all of these altitudes, how they are written, how their description and what they mean, can be found in your GSPRM in the introduction glossary section. However, I will also show you this table very briefly, just so you see what these all mean. And as you can see, we did see exactly these altitudes, which are the minimum altitudes or at or above altitude restrictions. And then also, I want to raise your attention to the third one from the bottom here, which is a recommended altitude. This is a very common question asked by instrument rating instructors and also examiners sometimes on your Jepsen chart. When you look at these SAM procedures, including approaches, remember that if an altitude is there without any line above or below or both, then simply it's a recommended altitude. It's not your constraint. And this will be everything for today. So thank you so much for tuning in. I wish you all the best with your exams. If you have any questions, as always, feel free to ask in the comments. We'll do our best to answer them. If you'd like to see more questions like this, then follow Airhead and go on a website and register an account. You'll see all of these questions and many, many more on different topics. And I'll be there to help you as well, replying to comments if you have any. Until then, I wish you all the best, and I hope to see you in the next video. Bye-bye.